This number, the sum of squared model, in other words, the difference between the total sum of squares and the sum of squared residuals, is equal to 10.88. That's not a number that we see in the sum of squares column of the ANOVA table. However, it's equal to the sum of the sum of squares due to VOR and the sum of squares due to log weight. In other words, these three numbers here do add up to the sum of squares total, so sum of squared total minus sum of squared residual gives us sum of squared model, which is then in this ANOVA table being further decomposed into the part of the sum of squares due to the model that's because of VOR, and the part of the sum of squares due to the model that's due to log weight. So this is just about 9, this is just about 2, this is just about 11. Those numbers add up. Now I'm going to run the equivalent regression. So I'm calling it M3 because it's the same model. It's the third model we're running, but we're going to call it .lm because we're going to use the lm function to predict log sleep based on VOR and log weight. So I'm summarizing that. And what we see here is the conventional regression output. We have estimates for the coefficients of the model we've specified. So that means we have an estimate of the intercept. We have an estimate for the coefficients for 4 of the 5 possible values of VOR, and there's 4 of 5 of them because one of them is the baseline. And then we have an estimate of the coefficient for log weight. These are coefficients that are being estimated regardless of whether I use the function LM or AOV, but the default for the ANOVA, the AOV function, is to show you the ANOVA table, and the test for whether each of those predictors separately is important. And the default for the LM, for the regression, is to show you the estimate of each of the coefficients along with a p-value that's specific to each of the coefficients. So I want to compare these. I want you to see how these compare. So to make them show up on the same screen, let me run again the ANOVA output here. And I want to compare this row of the ANOVA table, which is an f-test for whether log weight is an important predictor, whether it's a significant predictor, and this right here, which is a t-test for whether log weight is a significant predictor. These are exactly the same test. Note that the p-values are the same. They're essentially 0, but to be very specific, 5.17 times 10 to the negative 11. For any practical purposes, that's 0, but the point we're making here is the numbers are the same. And the t statistic is the square root of the f statistic. So if I were to take negative 7.633 and square it, I get 58.26. That's exactly the f statistic that's shown here. These are exactly the same test. Both the test summarized in this row of the ANOVA table and this test summarized in this row of the regression output are comparing the actual model that we specified to the same model if we'd left out log weight. In other words, it's comparing the model with both VOR and log weight to the model that has VOR only. The null hypothesis is that the model with VOR only is sufficient. So we see the equivalent tests shown in the ANOVA and regression outputs for log of weight. But for VOR, that's not true. For VOR, which is a categorical variable, a categorical predictor, the ANOVA table is doing a test for whether VOR matters at all. So let's start with the null hypothesis that we don't need VOR in the model at all. And that's what this p-value 0.02 is showing. That VOR is, we have a significant p-value, so VOR does seem to matter overall. We're testing the null hypothesis that VOR is not needed. But that particular p-value does not appear in the output of the regression because that question is not being asked as part of the conventional regression output. We're fitting the same model, but we're not asking the same question. Instead, the p-values that are shown here are testing whether each particular dummy variable, indicator variable for a particular level of VOR is necessary. So for example, this row here is a summary of a t-test for the null hypothesis that the coefficient for VOR being missing isn't necessary. In other words, if we left out the indicator for VOR being missing, but kept the indicator for VOR being herbivore, or for the animal being an insectivore, or for the animal being an omnivore, if we kept these predictors in here and just omitted this one, would our data be surprising? That's different than the test for whether VOR matters at all. This is a test for whether one particular level of VOR needs to have a coefficient other than 0 in the model. So it's the same model, but the tests that are being shown, the questions that are being asked are different. So this is relevant because you need to be sure that you ask the right, that you look at a test that is related to the question that you're actually trying to answer for your research project. If your research project is about whether a particular variable matters at all, any of the levels of it, then you're more interested in the output that is conventionally shown as part of the ANOVA. You're interested in f-test for whether VOR matters at all. Whereas, if you're trying to come up with a model that might include some of the different possible categories of VOR, but not all of them, then you want to be looking at t-tests for whether each particular category of VOR needs to have its own term in the model, or whether you can omit some of the terms but not all of the terms of VOR. You can also see that the f-test shown at the bottom of the regression output is no longer an f-test that's also shown in the ANOVA table. When we had only one predictor, this f-test that was at the bottom of the regression was identical to the one f-test that was shown in the ANOVA table. But now our ANOVA table has two different f-tests. It has two p-values in it, and neither one of them is identical to this f-test. So again, this is a case, an example of the two different default sets of output just asking different questions about the same model. So this f-test that I've highlighted here at the bottom of the regression output is doing the same thing that the f-test at the bottom of the regression output will always do. It's comparing the model we specified to the equal means model. So the null hypothesis is that the equal means model is sufficient. None of these predictors are needed. And then the p-value tells us how surprised we are by this data set if actually the truth is that we have an equal means model. And so what we're seeing here is we can definitely reject the null hypothesis that the equal means model is sufficient in favor of a model that includes the predictors that we've included here. That test is not part of the ANOVA output we have here. Here we have a p-value for whether VOR is important, and we have a p-value for whether log weight is important, but there's no p-value for whether VOR and log weight as a whole are an appropriate alternative to the equal means model. Remember that when we derived f-tests, we talked about comparing different pairs of models and calculating the sum of squared residuals from two different models in order to get to the f-statistic. That's what's going on here. Every p-value you see in either of these sets of output is comparing two models. Again, this f-test is comparing the equal means model to the model we specified. This p-value for log weight here or here is comparing the model we specified to the same model, just omitting log weight, etc. For any of these p-values, we can determine what the two models are that are being compared in order to generate the p-value. If we were to create the residual versus fitted value plot using the regression, we get exactly the same plot that we had using the ANOVA, because it's exactly the same model. We continue to see this model doesn't actually fit very well. Just as before, we can try to confirm the residual standard error. We can try to confirm the values that are shown in the bottom of the regression output. Remember, we calculated a moment ago this SSR3 based on the residuals from the ANOVA, but since those are identical to the residuals that we get from the LM output, we can use them here. If I take the sum of squared residual and divide by the degrees of freedom associated with the sum of squared residual, so it's 77, and take the square root, that's 0.3928. That's exactly the residual standard error, because that is by definition the residual standard error. So remember, we use the residuals to confirm this number. What we're saying now is this number divided by this number, which by the way is equal to exactly this number, is just the residual standard error squared. The mean square error is the residual standard error squared. So these are just different ways of showing the same thing. This row here is showing the same information as this row here. We can also confirm R squared. Even though the ANOVA table breaks down the sum of squares due to the model into the sum of squares that's due to VOR and the sum of squares that's due to log weight, R squared is still defined as the total sum of squares due to the model divided by the total sum of squares overall. So there's our 0.4781, that's right here. And similarly, we can confirm that adjusted R squared of 0.4442 if we run the appropriate function of the sums of squares. And just to make sure that you see it repeatedly, if we look at the fitted values that are generated by each of our sets of model output, those are the same numbers. right? So we see across each row the two fitted values are the same from the two models. That's exactly the same thing that we're doing in both cases. The only reason that we even have two separate functions, LM and AOV, is that in particular cases you might be interested in the questions that are answered by default as part of the regression output, or the questions that are answered by default as part of the ANOVA output.